If you recall, last week we introduced the idea of the derivative. The derivative of a function is what we can use to find the slope of the line tangent to a curve at a given point. So if f of x is a function, the derivative of f of x, denoted f prime of x, is given by the limit as h goes to 0 of f of x plus h minus f of x over h. The reason that we write this down is that we want to remember what we're trying to do with the derivative. This f of x plus h minus f of x over h, that's finding the slope of a secant line. The limit as h goes to 0 is where we move those 2 points close together and try to see what's going on at the tangent line. So this part, the fraction part, is the slope of the secant line. That's the slope of the secant line approximating the slope of the tangent line. We're choosing a point nearby, h units away. So the top is f of x plus h minus f of x. That's delta y. And the bottom is h. That's the delta x. So we're choosing a point on the curve to form a secant line. And we use that secant line to approximate the thing we're going after, which is the tangent line at one point. We want to see this f of x plus h minus f of x over h as rise over run, change in y divided by change in x. It looks like h because we can cancel out the x's. X plus h minus x, that's the run. Subtract the x's and we're left with h. The limit as h goes to 0, that's us shrinking the run down to 0 and seeing what happens. This is going to lead to a 0 over 0, which is indeterminate. We're trying to figure out which 0 over 0 are we going to get. Things we have left to do. Number one, figure out what this limit business is. This is very hand-wavy at the moment. We need to precisely define what we mean when we talk about limits. And more important, from a student standpoint, we need to figure out a shortcut to this process. So for example, if I give you the function x squared and ask you to find f prime of x, first of all, we know the shortcut. So we're like, all derivative is 2x. we do nx to the n minus 1, we know the derivative is 2x. If we want to get there using the definition of the derivative, then we have to do some algebra. I know everybody's favorite. It's like, oh, why would you want to cut out the algebra? It's like, oh, well, just for time purposes. You could do the algebra on your own time. It'll be super fun. But to use the definition, I would have to find the limit as h goes to 0 of f of x plus h. So that'll be x plus h squared minus f of x, which is x squared, and then divide by x plus h minus x will just be h. Now at this point, I can't make h equal to 0 because I'd end up with 0 over 0. That's indeterminate. That's what we're trying to figure out. But if we beat on this with the algebra stick for a little while, so we just play a little bit of algebra game. I'm going to take this x plus h squared and multiply that out. X squared plus 2xh plus h squared minus x squared all over h. So we're just going to play some algebra, mess around with some things. And what happens when I multiply this out is I get an x squared minus x squared, and those will cancel out. And this is what we were aiming for. We don't know why yet, but we'll see in a minute. Those two cancel out, and we're left with the limits as h goes to 0 of 2xh plus h squared over h. This is good for us because what we want to do is just let h go to 0, but that keeps giving us 0 over 0. But now in this form, with those x squareds canceled out, I can actually cancel the h in the denominator. I can look at the h, and there's an h in the numerator that I can factor out. I could take out, factor out an h, and that leaves behind a 2x plus h. This is helpful because now I can cancel an h out, and then h can go to 0. I won't have a 0 over 0. So now we can let h go to 0. And if h goes to 0, we get just the 2x. So at this point, we're thinking now that h is out of the denominator, now that h is out of the denominator, we can let h go to 0. So we just get 2x. Any questions? I did something very shady here. I wrote two things are equal that are not quite equal. And the only thing that's saving me is that I kept writing limit as h goes to 0. What two things here are not equal? In this last step, I canceled out h over h. When we simplify fractions by canceling out a variable from the top and the bottom, we're not making equivalent expressions. So this expression, 2xh plus h squared over h, is not exactly equal to 2x plus h. They aren't equal if h is equal to 0. Fortunately, we don't care because we care about what's the limit as h is near 0, not what's happening when h is 0. So for those of you who are thinking, these expressions are not equal when h is equal to 0. But that's okay, because we only care what's happening as h is near 0. We're not concerned with h equals 0, we're concerned with h near 0. This is very much a mostly dead situation. So the chocolates will work. In general, when you're called upon to use definition of the derivative, to find the derivative, someone is giving you some algebraic practice, your goal is going to be to cancel out this h. If you've got an algebraic function, your goal is to do algebra to cancel out that h. Once that h is canceled, you can let h go to 0. How's everybody okay? Everybody looks stoked because it's Monday. It's like, oh, it's Monday, calculus. Yes. I might be hallucinating that excitement, though. I don't know. Fortunately for our heroes, we have a shortcut. If we are looking at a power of x, we can just write down what the derivative is. If we can write a power of x, then we can just find the derivative that way. We get a lot of mileage out of this. Recall that the derivative is about finding the slope of the line tangent to a curve at a given point. So if, for example, my given curve is a line y equals mx plus b, we know that the slope of this line should be the same no matter what value of x we plug in. That's the whole defining characteristic of a line. The rate of change is constant. The slope is the same everywhere. It is its own tangent line. We can apply our shortcut. We can do the definition, but I don't want to. So we can apply our shortcut. We can write this as x to the n. I can think of mx as mx to the first power and I can read the constant b as x to the 0 power. If we can read powers of x, then we should try to read powers of x. So if y is mx to the first plus bx to the 0 power, we can write y prime is going to be 1 times m x to the 0 power plus 0 times bx to the 0 minus 1 power and we just get m. The derivative of a linear function is just going to be the slope. The derivative of a constant function is just going to be the slope, because a constant function is a horizontal line, and a horizontal line has 0 slope. We can also just remember that the derivative of a constant function is equal to 0. The derivative of a linear function is the slope. This includes constant functions. The derivative of a constant is equal to 0. That makes sense because a constant function has 0 slope. How's that, okay? Some of you have done that first powers and polynomials problems. And we were making all kinds of weirdo functions to get home this idea. The derivative of x to the n is nx to the n minus 1. Even if you've got some weird decimal exponents, multiply by the exponents, subtract 1 from the exponent. Multiply by the exponents, then subtract 1 from exponents. Two-step process. Multiply by the exponent, subtract 1 from the exponent. This applies to things like radicals. So if y is equal to the cube root of x, radicals are exponents. The index is the denominator. So this is going to be x to the 1/3. So y prime will be 1/3 x to the negative 2/3. Notice that I had a fraction exponent that's going to require some parentheses. I've also got a fraction coefficient that's going to require That doesn't technically require parentheses, but we're gonna put parentheses around it because we want to make sure that we are using clear communication. It is reasonable to expect that this expression without the exponent, without the parentheses around the 1/3, it's reasonable that a person will put the x in the denominator attached to the 3, even though it's not technically attached to the 3, except by half of our convention. So let's remove all doubt, put parentheses around our coefficient. If we have a denominator, we can write this as a power of x. Here the x to the 3 is in the denominator, so I can write this as x to the negative 3. So y prime will be negative 3 x to the negative 4. Negative 3 minus 1 is negative 4. Once again, it's not strictly necessary to have the negative 4 in parentheses, but it's a good habit to get into to make your communication very clear. We got to make sure that we've got single line syntax working so that we can text our friends during tests. I mean, so that we can type in things in Canvas and not have to use the equation editor. Obviously, during tests, you're just going to take a picture of your work and send them the picture, right? Make sure you turn your camera sound off because it's super suspicious when you're like sitting during the test and the camera goes off. My other favorite thing is when students would like write stuff on the inside of their, like, your calculator comes with like the plastic cover, right? The holster. And then some students are like, oh, I'm a genius. I can write stuff on this. So, well, that's kind of what it's for. But yeah, you could write stuff on this. But it's super obvious. Like you first of all, you think you're a genius. It happens a lot in high school. High school students think they're a genius, that no one's ever thought of this before. It's like, oh, wow, that's clever. Good job. And so they write shit on here. But during the test, it's like super obvious because which of these two, cover, calculator, which one should you be looking at? So I'd have like students be like, oh, and I'd be like, oh, Bob, the button's on the other one. Oh, thanks. I was wondering where the buttons went. I mean, there's another thing that I want to point out before we do a quick exercise. And in fact, we've already done it. If I've got a bunch of terms, no one even asked about this when I did this in the previous example. I've got a bunch of terms, so we'll just take the derivative a term at a time. The derivative of 5x to the third, 15x squared. The derivative of negative 3x squared, negative 6 x to the first. The derivative of 2x is just a 2. And the derivative of 11 is 0, which we won't write. Any questions? Comments? I have some practice problems. These are practice problems, and it's on a piece of paper. Make sure you write your name up at the top here. You can fill in a date. I needed balance. I needed name to be on this side and I needed balance, so I put date on the other side. You don't have to put date on the other side. I'm not even sure what the date is. I want you to find the derivative of the function. There are 6 problems. They're going to be powers of x. You're going to be able to use your powers of x. I've reminded you what the rule is, and I'm going to leave this up so you have an example. Use your notes. You can help each other out. Work these problems. A version of this will show up on Canvas for you to make corrections. But we're already turning this one in. If you when you find all 6, when you finish, just wait. I'm going to collect them all together. All right, pause right there. I have to say pause now. I can't say stop. So I'd be like, all right, stop. Collaborate and listen. We're gonna pass the pass papers to the front. So in your rows, just back to front and try to maintain rows. I'm trying to figure out who everybody is. And that requires collating lists. So please pass the papers forward. Once the papers are all passed forward, then you are dismissed. That's it for today. I will see you all on tomorrow. You have a good day. Hey.